maybe you remember in the 7-1 video when I said, I don't know why they throw this in here. This doesn't seem to fit. I'll figure it out though. This is why. Okay, something called logistic equations. And in order for us to understand how logistic equations work, we have to revisit exponential growth and exponential decay a little bit. Now, this is in your book on page 170, but I've only put up the first sentence. So if you screenshot the whole thing, that's fine, but try not to spoil the ending, if you will, okay? As you've learned a couple different times in your career, exponential growth is typically modeled by this, right? Y equals a constant times e to that change constant times time, all right? It assumes, here's the thing. It assumes that it can grow without limit. And in most cases, particularly when it comes to population, that's unrealistic. Our world cannot sustain a population that has unlimited growth, right? And so I want to model what that would look like. What I'm about to put up here, you do not need to write down. I just want you to kind of watch and pay attention and listen so you can understand what the idea is here, okay? If it were true that the population could grow without limit, what we'd be saying is that the change in the population, in this case y, the change you could just multiply it by some constant, and it would just grow and grow and grow and grow, right? That growth rate would continue to increase, therefore the population would continue to increase. That's what the assumption is, okay? And this is actually where this formula even comes from, okay? So if I integrate this is where I go, right? This is kind of the stuff that we've just been doing. And then we kind of move on. We raise all this to the e to those powers, and that's where this formula comes from. It's the idea that a population could grow without limit, okay? But that's just generally not true. And so now if you did read the rest of the paragraph, that's where it comes from. The growth rate decreases as the population grows, and there's a maximum population. So there's going to be some terminology you need to know. That capital M stands for the carrying capacity. And what the carrying capacity represents is the sort of upper limit or the maximum of the population, okay? And the logistic differential equation, and you need to know this, okay? This general form. So instead of it just being the change in the population is K times P, it gets balanced out by this carrying capacity minus the total population. M represents that maximum population. So as you approach M, what happens to the change in the population rate is that starts going down, okay? And so this formula you need to know, that's the logistic differential equation. And then the solution is something you need to know as well. Okay, so if we integrated that, and we're not going to integrate that, we're not going to go through those motions, you're better off just understanding that the population formula, the solution to this is this. Now what's important here, obviously we have an M up here, a T here, K is still a constant. What's important about this is in this equation, we assume that C is the starting value. That is not always true. In fact, most of the time it's true. Okay, so the C is not the initial amount. Don't assume that it is. Okay. And I'm going to draw you a little sketch of sort of what happens with exponential growth versus logistic growth. Okay, so this is not a perfect sketch by any means. It just gives you a general idea. Okay, so on the left we have exponential growth, just goes up forever. All right, for logistic growth, essentially what we have is a ceiling. And so once we approach that maximum value, the carrying capacity, that's as high as we can go, all right? And it kind of will stay there. Now it can dip as well, but that's the general difference. Exponential growth without limit, logistic growth with the carrying capacity. Okay, that's really the difference between this, and we're going to be spending a lot of time talking about this. Sometimes they will give you the carrying capacity. Okay, so we'll know M and other times they'll give you this equation, and you'll have to figure out what M is, but they won't give it to you in this form, right? So you'll have to sort of rearrange it to figure out what M is, and we'll go through one of those. Okay. So we're going to go right into examples. We're going to go through two examples, and the examples in your book, as you can see, have a lot of parts to it. So we'll start here with the very first example in the grizzly bears. So we'll see how they give us the K constant. National park capable of supporting no more than 100 grizzly bears. And it's not like, let's understand something. I don't think they're going around counting them and going, oh, we got 101, better take out, I don't know, what's a good name for a bear? Yogi. Yogi. No, you can't take out Yogi. He's a little smoky. Right. I don't think that's what they're doing. I think what they're saying is that naturally what's going to happen is something's going to happen. So there's not going to, whether it's, all right, old man Smokey's about to bite it over there, or like, all right, we only have so many places and they like attack each other or something. The food supply, absolutely. There's only so much that in this case it can take. All right. Now, so first off, what we've got to be able to do is figure out how can we write a differential equation. All right. So in the case of the differential equation, we need to know K. We need to know the carrying capacity. That's really all we need to know, right? It's going to be in terms of P. All right, so why don't you try to write that? Hopefully you got that. Right. So all I did was replace K with the 0.001, replace M with 100, and that would be our differential equation. Okay. So they have to give us a couple things in order to write the equation. Now, part B says the slope field for this differential equation is shown. Where does there appear to be a horizontal asymptote? Go ahead and write where you think the horizontal asymptote is. So where is it? Y equals 100. Y in this case is what though? P. Right. So our horizontal asymptote is the carrying capacity, right? Where that is when the population is 100. So the next two questions, what happens if the starting point is above this asymptote? So again, I like I said, my little rough sketch had a ceiling. It implied you couldn't pass through the ceiling, and but you can. It can happen, right? It can fluctuate. It's sort of like your oven temperature. When we set it to 450, that doesn't mean it stays 450 the whole time, right? It goes up above a little bit, then comes back down, and it keeps constantly readjusting and oscillating around 450. The same thing here. Okay, this population it's possible to have more than 100 bears, but in both cases, whether you're above the asymptote or below, you're trending toward 100 bears. It's going to either decrease towards 100 or it's going to increase towards 100. All right, and now go ahead and, if you didn't already, sketch a graph. If we start with 10, bears, so they always got to give us a starting point, right? Start with 10 bears, where are we going to go? Here is my graph that I made. So I started at 10 bears and just kind of followed the flow, right? And then kind of tops out at 100 there. Did you guys have something similar to that?
Yeah.
Okay. Still sticking with this question, but moving on to the next slide. So, did I skip D? Yes, I did skip B. I did skip D on purpose. I didn't want to make you have to integrate that. If you really, finding yourself struggling for something to do later on because you're just so bored, feel free to integrate it by hand. Yeah, no, I don't advise. All right, so here they give us the solution, okay? So what I would like you to do is see if you can solve this equation. They tell us though, what, did it have to be 10 bears? No. No, we don't even need to know that. We're solving for, for 10 bears. So if we start with 10 bears, that is what's going to allow us to find C. Okay, they give us everything else.
So we're solving for C? So we said
yes, we're solving for C. And then we're going to write the actual equation. So here we know what M is already. They told us what K is. Okay, so we know what M is here too. What we don't know is C. Okay, and we can find C knowing that at the start there are 10 bears.
Wait, so M is 10?
No.
100.
M is 100, right? M is the carrying capacity. So P is what we're going to have we're going to solve for
Is P 10? Because there's 10 bears. 10.
When is P 10?
So, but we said equal to
What?
0.
At time 0. So that's what we need. So we have this point 0, 10, so to speak. That we're gonna need that in order to find C. Eventually our equation, we're not gonna have an actual, the answer is this. We're gonna have equation P equals, and we're gonna have all the numbers filled in. So that over time we would be able to determine what the population was if we wanted to make that prediction. Our equation will have a T in it, all right? We're not gonna solve for T finally. We're gonna use our time to help find C, but eventually we're gonna have an equation with just P. There'll be, the only variable in it will be T when we finish, besides P. So here's where we kind of start, right? We plug in 100 for the carrying capacity, then the negative, okay, because that's the formula. The formula has a negative in it to begin with. Since we're talking about population growth, K will always be positive, but the formula has a negative in it. Just keep that in mind, okay? And so since I know that at the start we have 10 bears, what I can do is I can plug in 0 for T and 10 for P and solve for C. Now, I'm going to talk you through how I do this and think through it because I think it makes doing this a lot easier, all right? Here's kind of where we are right now. Since time is 0 at 10, this all becomes 0. E to the 0 is 1. So that's why this is just C. Here's the way I think about this, okay? I flip these around, swap these, because I like to think about this as a proportion. So those two can just swap. And so in my mind, I'm immediately going 100 divided by 10, which is 10, and I have 1 plus C equals 10, so C equals 9, okay? Now you can sort of do it a different way, all right? But that's kind of where the 9 comes from. Hopefully you got that, right? Swap these, divide the 100 by 10, and that's where this comes from. How many of you had C equals 9? Okay, good. Now, so my equation is just this, all right? So I plug the 9 in for C. Now I simplified this a little bit. You could have left it written out like that, but I went ahead and multiplied it just because I didn't want to do as much writing. So this would be my formula that I would use to predict the population in this national park over any period of time. What's interesting about this is that this bottom can never make this entire population go over 100. right? Unless this somehow was a fraction. Okay, so that's where that carrying capacity, that maximum value comes in. Since a slope field is a representation of a differential equation's solutions, and there are many solutions per differential equation, depending on what point you're starting at. So yes, this would be a solution under these circumstances for the differential equation that we looked at before. Okay? Now, it is asking us to find the limit of the population as time approaches infinity, as we march through time. Okay? And so really what they're saying is, as this value gets really big, what happens to this? So I want you to find that limit. What is the limit of the population? I mean, intuitively, you should kind of know what the limit should be, right?
100.
Should be 100 over time. Well, as this number grows, what happens to this term right here? Does it go to 0? Do you have any idea, or you're just saying that because you think it's supposed to be 100?
It's supposed to be 100, so 100's on top, so there's already 1 on the bottom, so it'll be like 1 over. It approaches.
So let's dig into this a little bit. Okay, as if this was a positive number, thank you for the digging motion. If this was a positive number, e to some gigantic number just is a gigantic number, right? So if it's in reality, this e with the negative power is 1 over a gigantic number. And 1 over a gigantic number is, of course, 0, right? It approaches 0. So that means this whole thing approaches 0, all right? Now, I will tell you, because I made your review yesterday for the test, there is going to be a question on your review that is not going to ask you about the limit of the population, but it's going to ask you about the limit of the change in the population, the rate of change in the population. And when we get there next week, we have to kind of do this first in order to determine that. So we'll get there later. All right. Let's move on to another part. Oh, it's the same question. When will the population reach 50? Okay. When is the bear population growing the fastest? So now what we want to do is solve for t. So I would like you to go ahead and solve this equation for t, please go. So again, my idea of swapping the 50 and the 1 and the denominator, so that's where the 2 comes from, 100 divided by 50, subtract the 1, divide by 9. Okay, e to the negative 0.1 t equals 1/9. Now, this happened the other day. I don't remember which lesson it was on. It must have been in lesson in 7-1. We talk about making sure to use the actual calculator value instead of rounding it to get the most accurate answer. And I would argue that maybe we shouldn't even use the calculator number. Maybe we should just leave it as the natural log of whatever, right? So in this case, when I take the natural log of both sides, and I think I thought some of you did this, just to leave it as the natural log of 1/9. There's no reason to punch that in and figure out what that is. And so when you do your calculation, you're actually doing, in your calculator, natural log 1/9 all divided by point, if that's our end result. And then if we have to use this later, okay, instead of using this number, I end up using this as my t, if you will, okay? And depending on what number of years we're trying to find, it's better to use all of this stuff in your calculator than to try to just continue to use the decimal value, because at some point I think the thing does actually round when you punch it in. All right, did we have that? Are we good on that? The years. So in 21.972 years, so almost 22 years, okay, we think the bear population will go from 10 to 50. Right, so that takes a while. Now, H is a different kind of question altogether. It's saying, when is the population going to grow the fastest? All right, and so what we're really asking is I want to know the maximum time for this. I want to know when the rate is the highest. I want to know when the maximum occurs for the rate of change of the population over time. Okay? Now, what's important here, this concept that I'm about to go through is important because this holds true for every type of situation, every type of logistic equation this way. Okay? Now, of course, what kind of equation is this? Do you know? Just by looking at it right now?
Oh. It's what's some form? No.
Nope. What kind of equation? Yeah. Hmm? It is not linear, actually.
Is it?
Cool. So if I multiply it out, okay, what kind of equation is it? It's a quadratic. Okay? And since my a value, if you will, right, on the squared term is negative, if I was to think about a graph, I would have some kind of graph that looks like this. Okay? It would be opening down. We know that because the a term is negative. And of course, since we're looking for a max, this also makes sense, right? If I had a quadratic equation that opened up, there would only be a minimum value. So in order to have a maximum value, it has to open down. Now, what we're going to look at are two different spots here. In one spot, we have no bears. At another spot, we have 100 bears. Okay, this is the rate of change. Let's keep that in mind. It's the rate of change. It does not reflect the actual bear population. It's the change in the bear population. Well, in order to answer this question, when the bear population is growing the fastest, I need to know how many bears are at this maximum point, right? So this is kind of what we're talking about. My maximum point is going to occur there. Since a parabola is symmetrical, how many bears are there at this point? 50. How did you get that? Yeah, you just split the difference, right? Well, we already figured this out. We figured out when we have 50 bears. Okay? And so that's where that comes in. Long story short, your takeaway needs to be when you're asked for the maximum population growth, when that is occurring, you have to know that it's half of the carrying capacity. That's when it happens. So for the future now, you don't even have to be asked for G, right? They can say, the question can be, when is the bear population growing the fastest? And you have to think to yourself, okay, when that occurs that occurs when there's half of the carrying capacity, okay? And that will always be the case because the logistic equation, that differential equation, is a quadratic. And in order to be a downward facing parabola, there has to be that symmetry. So the vertex has to occur when the x value, if you will, is half of the carrying capacity. Okay, that's the big takeaway. Questions? And it always happens like that.